Professors, I'm Gintaras Valinčius. I'm the neighbor of Physical Technology Science Center from another side of the street. I'm the director of the Life Sciences Center, and I have a privilege and honor to introduce our afternoon session, in which we will have a lecture by a world most prominent organic chemist from Denmark, Professor Karl Anker Jorgensen. Professor Jorgensen graduated from Aarhus University in Denmark in 1975, and he started his career in 1981. And after the graduation, he immediately accepted the position at Aarhus University. And in 1992, he got the professorship at Aarhus University. And the following year, he received one of the most prestigious awards in Denmark, the Bjerrum Medal. Most of you remember the famous Danish chemist, Niels Bjerrum. And in 1994, he became the leader of the Center for Catalysis at the Danish Foundation for Research. Professor Jorgensen, he's a recipient of numerous international rewards, including Lundbeck's Foundation Nordic Research Prize, Cornell's University Blomquist Award, the Knight's Cross First Class of the Dannebrog, and most recently Denmark's most prestigious Carlsberg Foundation Research Prize. Professor Jorgensen co-authored more than 300 peer-reviewed papers in most renowned international journals, chemistry, such as Angewandte Chemie, Journal American Chemical Society, Accounts of Chemical Research, and many, many more. And today, Professor Jorgensen will present his research, which covers organic chemistry and, most important, life chemistry. So, Professor Jorgensen, the floor is yours.
Yep. Thank you very much for this kind introduction, and thank you very much for inviting me here to this fantastic town. It's the first time I'm here in town, and I've really been looking forward to coming here, because being invited by students, that's for me the highest priority you have to take and come, because talking in front of students, that's the life of science. I will divide my lecture in 3 parts. I will start with something totally different, talking about you and your mirror image, and a little bit related to that. And then I'll move more and more towards science, chemistry. Then I'll talk about chemistry, what we're doing, a little bit of what we're doing. And then I'll finish up with, again, you and your mirror image. So you have probably all looked at yourself in the mirror this morning here, but I'm totally sure that very few of you have thought, who is it, me in the mirror, or is it someone else? And it's not you're looking at in the mirror, it's your mirror image. And your mirror image is different from you. Why? Because if you look into the mirror, your right hand is the left hand in the mirror. Your left eye is the right hand in the mirror. So, based on that, you're different from your mirror image if you look at you. However, if you look into your body, you're also different from your mirror image, because you have your heart to the left, your liver to the right. So, folks, you exist only as one mirror image. So you're unique, you're different from your mirror image body. Think about that. You have never seen your mirror image in real life. And how did it all start in terms of science? We have to go back to a glass of red wine. Many of you enjoy probably a glass of red wine. When you're drinking a glass of wine, sometimes in the bottom you can feel this, you can see these tartrate crystals. You're upset because you cannot drink the last part of the wine. But you have to be happy that the tartrates are there, and that people have been investigating these tartrates. So that's the salt of the tartrate, which you find in the bottom of the bottle. We have to go back to the 18th century, 1800 something, when this French Bio, he was looking at these tartrates. He only took the natural tartrates, and at that time, he was able to see through an equipment like this that they rotated the plant polarized light. Fantastic observation. But an even more fantastic observation, and the basic for modern science, in life science, was done by this guy up here, Louis Pasteur. He was also interested in tartrates, but he was not interested in natural tartrates. He was interested in tartrates produced by chemists. And he was able, when he looked through the microscope, to see that there was not only one crystal, there were two crystals of these tartrates. And you see them here, they were mirror images of each other. And it was a fantastic discovery, because he was able to separate these mirror images of these tartrate crystals, and one of them rotated the light in one direction exactly as natural tartrate, while the others rotated in another direction. And based on that, he said that life has a preferred rotation. It took 50 years before people realizing what was the basic for this. And it was when the structure or knowledge of how carbon is built up was made. That if you have carbon built to 4 different substituents or groups, these molecules can be mirror images of each other. Such molecules are called chiral. The word chiral comes from Greek hands. Your left hand is a mirror of the right hand. They are the same, but not the same, because if you place them on top of each other, they're different in 3 dimensions. So chiral molecules can exist in mirror image forms, but in all living cells, it's only one of the 2 mirror image forms which exist. Just like you also exist as one mirror image form. And this is really fantastic and has enormous consequences in life. I'll give you an example here, which dates back to the late 50s. At the late 50s, the chemists at that time, they were not as good as we are today. So the German pharmaceutical company, Grüntal Chemie, they put on the market a drug named thalidomide. But the chemists at that time, they could only synthesize thalidomide as a racemic mixture, where you had both enantiomers, both chiral forms of thalidomide. They introduced thalidomide to the market because they have found out that it had some interesting and positive effects on especially pregnant women. It reduced morning sickness and discomfort. But they were not aware of the difference between the 2 left-handed and right-handed molecules of thalidomide. So it was an enormous catastrophe. About 10,000 kids was born with this, without hands or legs. Why did that happen? Because at that time, you did not investigate the different properties of the different molecules being here. It was an eye-opener for the whole industry, all life science, how important it is when you're giving molecules to living cells, humans, or whatever, that you really know how they interact in the living system. Because one of the molecules here, the left-handed molecule of one of the previous slides, interact in the expected manner, reduced morning sickness, discomfort for this pregnant woman, whereas the other right-handed molecule of thalidomide, it reduced the blood supplies from arms and legs. So therefore, it's important to be able to control the formation of only one of the 2 mirror image molecules. And catalysis can do it. When your father's spermatozoa hit your mother's egg, a catalytic process started when the spermatozoa entered the surface of the egg. So there starts catalysis, the catalysis of life. And if you look at life is catalyzed by a fantastic cascade of enzymes catalyzing all the chemical reactions taking place in your body, and it stops the catalysis of your life when your heart stops beating. But these enzymes exist only as one of mirror image molecules. So it directs it towards only one stereoisomer being formed. And this is very important. And the role of catalysis cannot be overestimated. 70% of the nitrogen atoms in your body and also in the newborn baby here with her mother. 70% of these nitrogen atoms are made by one catalytic process, the Haber-Bosch process. 70% of all the products we are surrounded with is made by catalysis. 20 to 25% of the world economy directly or indirectly relates on catalysis. So it's an important field, catalysis, which we are in here. So if you want to make chiral molecules, where you want to make one of the different mirror image molecules being possible, you can do it by several ways. You can do it by enzyme catalysis, the chemistry taking place in our body, which can be moved into laboratory. You can do it by metal catalysis, a field which was extensively developed in the late part of the last century. We were involved in that also. But in 2000, we took another step in my research group. We went to organocatalysis. The reason for doing so was that at that time we were beginning to see that reactions taking place in enzymes, there was some resembling that we might be able to do this with small organic molecules. So two of us who were involved in the start of organocatalysis, David Macmillan at that time at Caltech, and us, we came from a metallo-organic background, were interested in enzyme-like things, whereas Barbas and also Ben List, who were at that time working at Scripps, they were looking at what happens on the surface of catalytic antibodies. And what they realized was the chemistry they could do on the surface of, based on the surface on catalytic antibodies, you could do it with very simple organic molecules. I'm a chemist. And a chemist, you have a privileged situation because you create something. You make something with your hands. As a chemist, we're making molecules. So in order to make molecules, you have to be creative because you have to make bonds in a new way. You have to break bonds in a new way if you want to move the field. So to a certain extent, I feel that as a chemist, we're in the privileged situation. We might compare what artists are doing because artists, they're also being creative. We see here to the left 4 well-known artists creating music. So they're breaking the borders of how to make music. The average age of these, or the total age of the 4 members of Rolling Stones, I'll ask you, below or over 300 years? A question for the audience. They are only 299 years old, the 4 members of Rolling Stones here. But also Giacometti, you see here to the right, also creative, breaking the borders of making sculptures. And my chairman, he asked, oh, can I say something about your future? He didn't say it, so I'll say it here. I didn't start out as a chemist. My interest when I was a little bit younger than you was studying chemistry. The weekend, before I entered the university, I didn't spend that time thinking of that Monday morning I had to start at Aarhus University. No, I was attending the Nordic championship in athletics, and I won the decathlon. So I was up in Finland. I had promised my mother to travel home. So I received the gold medal for being Nordic champion in decathlon, and then onto the plane back to Denmark, started Monday morning at the university. I didn't spend much time the first 6 years at Aarhus University doing chemistry or physics. I was traveling around representing Denmark in decathlon, 110-meter hurdles, and I was using the main part of my time training and competing. In the summer 1981, I was attending the European Cup in Malmö in decathlon, and I looked back over the stadium because I realized it was over. Doing decathlon, you have to train 6 to 8 hours per day, every day. And I was beginning to have challenges with my body, been training for 8 to 10 years, that amount of time. Also, there was one of the professors who took me aside, hey, you're doing quite well in sports. What will you do when you finish? And I realized that I had to do something else. So he said, you might tried to think about doing a scientific career. So he encouraged me to take a PhD. I got a PhD a couple of years later, and then I went to do postdoc with Roald Hoffmann. Roald Hoffmann, who you see here to the left, he was the one who introduced molecular orbitals in chemistry and physics. I went there a couple of years after he got the Nobel Prize. He was still in the 40s at that time, and it opened my eyes for doing science in another way. I came to a group very open-minded, where the professor was working for the students, and as a student postdoc, we were working with the professor, Roald Hoffmann. I'll come back to that later. So it changed the way of, at least I looked at science, and the way that is still, we're trying to do science in my research group. So I came back to Denmark, and in 2002, we changed our research doing organocatalysis. We were a couple of people doing that, and we were being considered as being crazy. So the next couple of minutes, Rammstein. What is the relationship between doing organocatalysis and Rammstein? When we were starting doing organocatalysis, we were the 3-4 crazy people standing in row going to a Rammstein concert. Now organocatalysis is one of the fields in making chiral molecules. But there are several other reasons. If you want to have a job, if you cannot have a job after your PhD, you can apply for the Rammstein, because they have several PhDs in chemistry working for them in their company, making all the fireworks when they're playing. There are also a couple of other reasons. I have friends in the music business. I have one of my closest friends. He's the one traveling around with rock bands as chef, serving these rock musicians backstage. So I have for years been traveling around with Rammstein as dishwasher. So I'm the one helping my friend when he's out with rock bands, dishwashing backstage, for example, with Rammstein. As Rammstein, several of the musicians are saying, we have the highest qualified dishwasher on the road in rock business. Can I speak for a few more minutes, if possible, about this? Should we take one more Rammstein story? Okay. A couple of years ago, I was together with Rammstein and Slash from Guns N' Roses. So it was a fantastic day and an open venue, backstage, very closed area. And Slash, he was sitting out there playing acoustic guitar, for an hour. The sun was shining, backstage. Wow, this was really fantastic. And serving rock stars backstage, you'll fly on the wall. So I went to see Slash playing, because he was playing before Rammstein was going to play, and it was really great. So after he was playing, he came in backstage, should be served. I was just standing there doing some things at the buffet, and then he put his hand on my shoulder. Chef, I need some help. I said, okay. I can tell you, Slash's hands are very strong. Fingers are very strong. I'm allergic to fish. I can see there are fish on the table here. Can you help me? I told him, Slash, I'm not the chef here. I'll call in the chef who can help you, because I will not be able to tell a fish from a piece of meat. No. You're the chef. I've seen you. You walk around like a chef. You're not wearing the same clothes as those preparing the food. So you're the chef. I need help now. I'm hungry. And then he pressed even harder. Said, no, Slash. The chef is out there. He's coming in. No, you're the chef, and don't mess with Slash. And I can tell you, then the blue marks were starting on my shoulder. Then the keyboard player from Rammstein came up, puts his hand on Slash. He was just sitting down there and was listening what Slash was saying. Don't play with our dishwasher. He's a very good chemist. Don't play with him. So you can end many places when you're doing chemistry. But let us go back to organocatalysis. What is organocatalysis? That's using small organic molecules. You can do stereoselective reactions, multiple activation modes, and you can discover new reactivities, new chemical reactions, and you can also have easy reaction conditions. So now I have to introduce to you how do we make a stereocenter. So if we have a flat molecule here, and you can make either the left-handed molecule or the right-handed molecule, the part B can come in from either the left or right. That was what Grünthal Chemie did. They had a racemic mixture, problems. But on the other hand, if you shield one of the faces here, by, for example, that's what enzymes are doing, other catalysts, then B will come in to the right, and then you form one of the two enantiomers. And that's what we're doing. That is the simple chemistry we're doing. I'm coming from Denmark. In Denmark, we have a company. I played with the bricks when I was a kid. My kids played with it, and now my grandkids are doing the same. They're playing with Lego. So what we're doing, we are just preparing molecular Lego blocks. But we're controlling only making one of the two enantiomers of these Lego blocks. So we are preparing the Lego blocks for various companies, academic to use, so they can make the molecule they want, shown here by the helices. And now I'll turn to chemistry, because I'm a chemist. So I'll go back to fundamental activation modes in chemistry. If you have an aldehyde up here, and in the beginning of organocatalysis, every time we had to develop a new reaction, we had to put a lot of effort in developing a new catalyst. I had a PhD student, Mauro Marico, Italian PhD student with Italian temper, and a German postdocs, very quiet boxes. They two were a fantastic pair. And they were so upset that, oh, now if we have to develop this reaction, we have to develop this catalyst. And then the German postdoc said, let us sit down and try to understand what's going on. And they did so. So they took an aldehyde, they took a secondary amine here, and then they could see that it first formed the iminium ion. Then you have a proton here, which can be removed, and then you get the N-amine. You're generating a nucleophilic carbon here, which will react with an electrophile. You form the stereocenter, because you have a stereocenter up here, and then you have the product. The problem with this reaction was, if they added 10 mole% of catalyst, they had less than 10 mole% of product here. So not a suitable process to be used by others. But they had very high enantiomeric excess. I'll come back to that in a moment. But they also saw, by looking at this night after night on NMR, that there was this intermediate being formed, nucleophilic attack of the oxygen into this position here, which was a side track where the catalyst was trapped, and similar here. So they came up with the idea that maybe we should protect this hydroxy group here with a silicon, and then we'll block one of the phases, and then the electrophile will approach from below, and we form a stereocenter in the alpha position to an aldehyde. This was a very clever trick, very clever, done by a PhD student and a postdoc. And now you can buy these catalysts, the diaryl prolynyl cellular ether catalyst. Here are various combinations with aryl group, alkyl groups, and several others. This is an example from the first batch produced by Sigmund Aldrich. It's used in milligram, gram scale, and also in ton scale. Half a kilogram of the catalyst cost in China 10,000 euros. So it has changed the way of doing catalysis when you're working with a variety of different compounds. I'll give you some examples. If you take an aldehyde, one of the most fundamental compounds in organic chemistry, you can put into the alpha position of an aldehyde an alkane by reacting it with a nitroolefin, or an enone, then you have a carbonyl here. You can have phosphate. You could put in an aryl group. You can make the manic reaction controlling two stereocenters. You can do alpha amination, alpha hydroxylation, alpha sulfonylation, selenation, fluorination. I'll return to that in a second. And then you can put in all the other halogens. High yield, high enantiomeric excess. So I'll focus a little bit on how to put in, for example, fluorine in the alpha position of an aldehyde. Why is this reaction important? It's basic to be able to do so, for example, in the pharmaceutical industry, agrochemicals, PET tracers, when you want to look at how the molecules are distributed in the body. So you take a simple aldehyde here, you take NFSI, electrophilic fluorination reagent, catalyst loading down to 0.25 mole%, then you introduce the fluorine in the alpha position here, good to high yield, more than 91% enantiomeric excess, and enantiomeric excess is one of the goals here. 90% enantiomer excess means you form 95 of one of the mirror image isomers and 5% of the others, and then you calculate the EE based on this. I'm also showing this slide to tell you a little bit about competition. As a PhD student, many of you probably think, I'm the only one doing so. Yes, sometimes, but this was and still is a very competitive field. So you can see here 3 groups published within the same days, the same work. We used the TMS prolinol catalyst, Macmillan, and Barbas, they used the Macmillan catalyst for doing it. Let me take one more example of the alpha fluorination, just to show you how it has been expanded by our group. Here's an example where we first do the fluorination, we put in fluorine here, and then by mixing these 2 other compounds in, we put an alkyne. Why is it interesting to have a stereocenter here with an alkyne and a fluorine, and then being able to vary the R group here? Because a lot of the compounds you see here have this motif, and this is very important for the biological activity. And I'm showing this one here in a bracket here, because we can form this in one reaction, and then we have this important intermediate for the pharmaceutical industry here. But this catalyst is not only restricted to aldehydes. You can also take alpha-beta unsaturated aldehydes, and then you can put in nucleophiles in the beta position. Malonates, amino acids, alkenes, alkynes, aromatic compounds, and so on. You can do cycloaddition, deals all the reaction, 1,2-D dipolar cycloaddition. You can do epoxidations, I'll return to that in a moment, acidination, cyclopropionation, and then you can put in a lot of different heteroatoms and metals in the beta position of alpha-beta unsaturated aldehydes. I'll give you, again, only one example here, and that's the example with the epoxide, because it's basic chemistry we are playing with here. So we can take an alpha-beta unsaturated aldehyde, hydrogen peroxide, the TMS-protected prolinol catalyst, and then we are having these epoxy aldehydes here. High yield, high diastereomeric ratio, we are forming 2 stereocenters here, and very high enantiomeric excess. So you have the catalyst here, you form the iminium ion, now you generate an electrophilic carbon here, reacting with a nucleophilic oxygen in hydrogen peroxide, forming the carbon-oxygen bond here. Nucleophilic carbon here reacts at the electrophilic oxygen, and then after hydrolysis you have the product. It's a widely used reaction, it's a textbook reaction now. And here 3 examples from the Nicolau lab where he's introducing 2 stereocenters in very complex molecules based on this chemistry here. For many years we thought that this was the mechanism, this was the way these epoxides were formed. But last year we published in collaboration with Matthew Vetikart in the United States, based on very advanced NMR studies and labeling studies, that this is probably not the reaction mechanism going on. We could find that there's an isotope effect, carbon-13 isotope effect on this position here at the carbonyl, as well as here. So we introduced this as a new intermediate. So maybe one has to rewrite how these reactions are proceeding based on such an intermediate here. But these catalysts have also opened up avenues for other types of activation modes. The first 2 activation modes here were the classical activation modes. So what were we doing in the second activation mode here was that we took an alpha-beta unsaturated aldehyde, formed the iminium. But if we have a base here, we can remove the base. Then we have a dienamine, not known before 2006 when we published our first paper. And it opened up for making new types of cycloadditions. And also what we call dual activation strategy, because you have an electron-rich system here, but if we put a hydrogen bonding donor in the alpha position to the nitrogen here in the pyrrolidine ring, we might be able to direct reactivity. I'm showing this because it also integrates another part of the chemistry we're doing, computational chemistry. I'll also come back to that later. So here's an example where we take alpha-beta unsaturated aldehydes, we take an alkene, and now we have this hydrogen bonding square amide here, and then we can form cyclobutanes, a 2+2 cycloaddition, where we're controlling all the stereochemistry. But we have the dienamine here, we have the nitroolefin here, coordinating hydrogen bonding to the square amide here, directing the carbon towards this carbon here, so a 2+2 cycloaddition, and here are calculations. So we are adding now calculations to our work in order to understand what's going on. But let me now move from chemistry being done in microgram, maybe gram scale, and move up in scale. Normally when you want to make advanced compounds, complex molecules, for example, you do this stop-and-go synthesis. You mix two reagents, a new product, two other, a new product, then you mix these two products, and then it goes to the final. But organocatalysis has opened up for a new way of doing it, because you can do one reaction, you don't need to clean, purify things, which you very often have to do here. So you can do it in a consecutive manner. And this, we have done it for a couple of reactions, but the first breakthrough for using this in industry was done by Merck, for making this compound here, which is a very unique compound according to Merck for the treatment of migraine. And they used organocatalysis for doing it. They used the cascade, which we have introduced, where they start with this difluorobenzene here, bully, and this acrolein here, forming this intermediate, rearrangement reaction to this allylic alcohol, oxidation, and now it's in 10,000 liters of solvent. In another container, they take the unprotected catalyst, treat it with TMS chloride, you protect here, and then you introduce the stereocenter here, and then you go on to the intermediate to the final product. The challenge in the industry is the number of operations. If you're moving around with 10,000 liters of solvent, it's not easy. So the number of manual operations here is 7. The yield per bond formed is 94. Yield per manual operation is 97, and purification factor is 4. And on the next slide, 4 more examples of compounds on the market where there are now patented processes based on the TMS-protected prolinol, the Tamiflu here for treatment of bird flu, Insectivec here for treatment of hepatitis C, paroxetine, antidepressive compound, aliskiren here by Novartis, which is for hypertension. Based on organocatalysis, patent process in kilogram, maybe ton scale. But let me move it to another direction, because you can combine organocatalysis with metal catalysis. I've been introducing to you enamine, iminium, and dienamine. Now I'll merge these two together here and see how they can work together with Lewis acid, palladium, iridium, and also different types of oxidation reagents. So it's another aspect of the chemistry which we have been developing. It all started in a different way. A couple of years ago, we introduced also a way of making these 14 beta steroids, attractive compounds for various pharmaceutical industries. What we started with was this compound up here, where you have an alpha-beta unsaturated aldehyde. Then you took the TMS-protected prolinol catalyst. Then you formed the dienamine set up for a 4+2 cycloaddition, forming in one step this intermediate here. You can do various other things with it. But we became interested in, okay, what about this motif? Can we use it for something else? And this is here. So if we now form this intermediate here, we might have in the gamma position the ability for direct reactivity towards the gamma position. And now we are combining it with metal catalysis, classical metal catalysis, allylic system here, generating a system. So one catalytic system here, another catalytic system here. So we can either, in the case of iridium, form 2 stereocenters. In the case of palladium here, 1 stereocenter. And there are a lot of challenges here. I'll not go into the details, but you can have 2 compounds here, 2 products, depending on how you mix your system. So if we take this simple catalyst here, this phosphine amidite here ligand, which coordinate to iridium, you can see you cannot control the gamma to alpha selectivity. This is the product we want. This is the unwanted product. We have good DR, or we don't have good DR, we have good EE. We can improve by taking this chiral ligand, this is a non-chiral ligand, then we are improving the parameters here. But we can design the system so we can control both the gamma to alpha selectivity, stereoselectivity, and enantioselectivity. And here's the next, this is just some results showing that we can combine this by obtaining these different classes of products, depending on if we're using iridium, then we have the product here, or palladium, then we have the product here. High yields, high stereoselectivity. Another example, before I move on to something totally different, is also where we are combining palladium and organocatalysis, forming these attractive compounds here. Again, a building block with various applications in, for example, life science. So we again merging two catalytic cycles. Here we have the organocatalyst, the alpha-beta unsaturated aldehyde, forming the iminium here. Now we have a mashed system here, a carbonate. We open up the carbonate by palladium. We protonate this nitrogen here, release of CO2. Then we have generated a nucleophilic nitrogen here, adding into this position here, and then we have the product. And here are some examples. It works with high yield, but we can reuse the palladium in the second step, doing a coupling reaction here, obtaining this type of product. I'll show you how we can move borders of reactivity. Normally, when you're doing polar reactivity, you react a nucleophile with an electrophile, you form a nucleophile electrophilic bond. So the nucleophile electronegatively charged, the electrophile electropositively charged, they will be attractive to each other. This is, if you want to do enolate chemistry, you take an aldehyde, then you can form an enolate, you generate a nucleophilic carbon here, which will react with an electrophile. And we have for years been using enamine chemistry, generating a nucleophile here, reacting with an electrophile. What happens if you want to have two nucleophiles to react with each other? They'll, of course, repel each other because they're both negatively charged. So coupling of two nucleophiles is a challenge. But what happens if we can take a nucleophile activated by an organocatalyst, then generate a system which we can oxidize to an electrophile, now reacting it with a nucleophile, forming a nucleophile-nucleophilic bond. So we're generating a principal, a carbocation here, and then adding a nucleophile. It started in a different area. With the systems you have seen before, and non-wanted reaction. But again, the PhD students in my group, they have been taught undesired products are often much more important than desired products. So they were looking into this system here, and they realized that they had a coupling reaction. Two of these molecules coupled to form a new carbon-carbon bond. And what was going on, we had the iminium system being formed, the dienamine, which we saw on the previous. But one day they used copper. They wanted to do a total different reaction. So they found out that when they had copper and the presence of oxygen, they could oxidize this specium here to a radical, and then a couple of forming a new bond here. And that if you have no organocatalyst, if you cannot activating the system, no conversion, no copper, low conversion, no air, only the amount of copper here determines the amount of product being formed. So it opened up at least our eyes for maybe we can move reactivity into a new dimension. So we can couple two systems here, good yield, high enantiomeric excess, high diastereometric ratio. We can have different substituent patterns for the cyclic system, acyclic system. We can also do heterocouplings. But when we tried to move it to something else, we were really surprised, because one of the byproducts we observed was that if we take this aldehyde here, alpha-branched aldehyde, an organocatalyst, primary amine, and silver as the oxygen, we generate a carbocation here, which reacted with a carboxylic acid, now forming this carbon-oxygen bond here, according to our knowledge, never seen before. It works for this system here. For electron-rich system, you can see high yields, high enantiomeric excesses for these aromatic carboxylic acids, also aliphatic carboxylic acid. We can move around with the substituent pattern here as well as here. All cases high yield, over here moderate enantiomeric excess. And now we are moving this in a new direction for making bioconjugation, as you can see here. We're moving it, but now we are forming this intermediate by other means, and now we are coupling amino acids, where we have a stereocenter, dipeptides, tripeptides, even small proteins we can couple in to the alpha position of an aldehyde. And the most important part, here you have the catalyst here, and it determines the stereochemistry here, because if we use one enantiomer of the catalyst, we have one product. If we use another enantiomer, we have the other stereoisomer. So the catalyst determines what's going on the center, stereocenter we have formed, and that is important by moving this into bioconjugation. This was an example of how we are now being able to react molecules which normally will repel each other by combining organocatalysis with other types of chemistry. I will finish my scientific part showing how to move the borders of cycloadditions. A couple of years ago, we became interested in, that was Rasmus Mose together with two others. He became interested in if we take cyclopentanone here with the primary amine catalyst, and we could generate this cross-dynamine here. We could do a 4+2 cycloaddition, forming these NOR-camphor scaffolds. Again, legal blocks, molecular legal blocks for making important drug candidates. We're not interested in making the drug candidates. We're interested in making the chemistry, developing the new reaction here. So here are examples. Nitroolefins, enones reacts very well. And next time you're having a gin and tonic, remember the bitter taste in tonic comes from the cinchona alkaloid. So here is a modified cinchona alkaloid where we introduced the primary amine, activating the system, doing the generating this cross-diene intermediate. But Rasmus Mose, the PhD student, he did one reaction too many. Probably one of the most important reactions we've been doing over the last couple of years, because he also took tropone here, and to his surprise, he got the 6+4 cycloaddition. So now we go into the world of cycloadditions. And I go one step back. And I go back to my postdoc advisor, Roald Hoffmann, from the Woodward-Hoffmann rules. My postdoc was more than a scientific postdoc stay. It was also the development of a long life, very near friendship with Roald Hoffmann. So Roald, together with his wife, spent several times for the last couple of years in Aarhus during the summertime, because Roald's wife, Eva, is from Sweden. So when we developed this chemistry, when we had this reaction running here, it was when Roald Hoffmann was staying a summer with us. So we said, Roald, what about these 6+4 cycloadditions? That must be something of interest to you. Do you have a 6+4 cycloaddition? Yes. Wow. So here's the story. Normally you do 4+2 cycloaddition. The Woodward-Hoffmann rules tells us number of electrons, 4n+2, n equal to 1, 6 electrons, then you have the classical Diels-Alder reaction. Well known. But if you move to n larger than 1, you're really facing challenges. It's not easy to do these high-order cycloadditions. They were said to be possible to be able to perform in this paper by Woodward and Hoffmann from 1965. I'm showing this. This was how they submitted one of the 5 papers to JACS in 1965, showing that by endo and exo cycloadditions for the 6+4, yet unobserved, symmetry allowed 6+4 cycloaddition. So when we entered the field, there was no way to control these reactions here. So we thought, okay, are we now moving the borders of cycloadditions? So we asked ourselves, okay, how easy is it to move the borders? So here's the cover from Angewandte from 2017. Why is it so challenging to move from 4+2 cycloadditions to 6+4, 8+2 when we are in the 4n+2 regime of cycloadditions, n larger than 1? And if you look at the frontier orbitals over here, that deals all the reaction, many of you probably looked at how to draw the orbitals for 4+2 cycloaddition, but they look quite simple for the 6+4, 8+2, but they're not easy to do in the lab. And if you are able to do the 6+4 and 8+2 cycloaddition, you should open a bottle of wine, which we're doing here. So here are one of the first reactions we did. So we take the cyclopentanone here, 5-membered ring, tropone, X equal to oxygen. Then we are forming, via the organocatalyst, we are forming this cross-dienamine. We have the 6+4 cycloaddition. If we expand the ring size here to a 6-membered ring, we have the 8+2 cycloaddition, undergoes a rearrangement reaction to the 4+2 cycloaddition product. So let me just show you the catalyst here. It's again this primary amine catalyst, X equal to oxygen, high yield, good yield, high DR, high enantiomeric excess. And now there are two activation sites. The cyclopentanone here is being activated by the organocatalyst. We also have to protonate the nitrogen here in order to direct tropone to give the desired reaction. If we move to the cyclohexanone here, we form this linear dienamine as intermediate, and now we have a good fit. We're going to make a bond between this carbon here and this carbon, and the red and the blue here, and then we have the 8+2 cycloaddition, which can, after catalyst release, give you the product. There's also a lot of other chemistry being involved here, but I'll not go into detail with that. It also opened another field of our research because we were contacted by Ken Haug, UCLA, said, wow, you're doing 6+4 cycloaddition. This was what Woodward asked me to do in the late 60s, but now you're doing it. So let us start looking at this together. So we started doing calculations. Here's one of the examples on this reaction. Here we have the cross-dienamine, the calculation. So this is the most stable intermediate compared to the linear one. We have to protonate the nitrogen here. But we also became interested, what about the counter-ion? Does it have any influence on the selectivity? So we took different chiral acids here and showed that there was no selectivity dependent on the counter-ion. So it's only the proton which is important. And why does this proceed as a 6+4 and not as a 4+2 cycloaddition? So here we have the catalytic intermediate. Now it's pure computational work. The tropone, the oxygen here, coordinates to the proton here, giving us this intermediate. First, we have the first bond being formed here, the transition state, carbon-carbon bond formation, giving us an intermediate which we had been able to isolate and characterize. Then we form the second bond in a lower transition state. Then we have the 6+4 cycloaddition, the exoadduct as proposed by Woodward and Hoffman, and a much higher transition state energy is for the classical 6+4 cycloaddition. So we were very pleased that we now begin to understand this. But this is a conference where you're using femtosecond spectroscopy. So we are now doing, so I'm listening to some of the lectures this morning, I decided to put in one more slide. Because now we are doing studies of how does this proceed in the femtosecond regime. So here we have the reaction again. Here we have the two compounds. Now the tropone is activated here. And now we are doing dynamics. So it's hard to see how the molecules here are moving around. So we have the oxygen here with the tropone, the one here. It has to find the proton here to be activated and see what happens. Femtosecond. Every movement here is a femtosecond. See, now they're beginning to be aligned. So we are moving towards this complex here and see what happens. Now we are moving up along this barrier here. We form the first carbon-carbon bond here in a few femtoseconds. You have it here. So now we're over here with a much lower transition state energy forming the second one, and now the system relaxes. So here we are doing molecular dynamics. It takes 111 femtoseconds to go from the left to the right here. So moving experimental chemistry via computational work in a new direction, understand what's going on in these complex systems. And we are moving it even further. If I can, here. Because here we have another system where we have a carbonyl here. There should be a move, it's unfortunately not working. So we're generating an 8-pi system here, and if reacted with an olefin, it will react to these two positions in a stepwise reaction. The movie should show a stepwise reaction. And we can again here control the diastereoselectivity, high yield, high enantiomeric excess. So 8+2, 10 electrons, 4n+2, n equal to 2. But during this work here, based on computational work, so here's the transition state for the first carbon-carbon bond formation, stepwise reaction. We have formed the bond between this carbon and this carbon here. Then we have the nitronate. We have a negatively charged oxygen, which might add into this position here, giving us now the 10 plus 4 adduct here, 10 plus 4, n equal to 3 in the 4n plus 2 rule. It can either go at 3 sigma-tropic shift or going back, forming the product here as we observed. But this intrigued us. Can we do 10 plus 4 cycloadditions? And this we can do. So here's an example where, based on the computational work, that if we put an aryl here, then we generate an intermediate like this. We have a 4 pi component here, and then we are making 10 plus 4 cycloadditions. And just to show that it's not working for just one compound, it works for a variety of different compounds. You can vary the aryl substituent here, high yield, high DR, high enantiomeric excess. You can also vary the substituent pattern here, the same results obtained. You can also vary the substituent pattern either here and here. So it's diversity oriented. And we have moved the borders even further. For here, heteroaromatic compounds, very important compounds in organic chemistry as well as other fields. So if we move this compound to here and take pyrrole, we have a pyrrole here. We treat it with a secondary amine catalyst. Then we are forming the iminium. We can see this by NMR. We remove the proton here by a base. So now we have generated a 6 pi system here, nucleophilic nitrogen here, which will add either into this 4 pi component or 2 pi component here, generating these classes of product, which are very important product for the life industry. So we're trying again to move the borders of chemical reactivity. But we're not only doing that, we're also trying to move it. What happens with bioactivity? Can we do bioactivity studies in combination with developing of new reactions? Here's an example where we're having tropone, have a lot of different activities. That's the challenge. But if you begin to build molecules upon this tropone, you have again interesting compounds with bioactivity. So we set up, could we develop a new 4 plus 2 cycloaddition using other catalytic concepts, forming these products here because we thought they were interesting. So here's the concept. We take this compound here, treat it with a base, a catalytic base, removing the proton here, generating this 4 pi system, which will undergo a 4 plus 2 cycloaddition, and there are different types of products being formed depending on the substituent pattern. I'll not go into detail with that. Just showing you that by being able to control this, we can begin to control bioactivity. So here's an example. This is the most reactive intermediate based on some assumptions on the previous slide. So it's exclusively found as this one, where a nucleophile from, for example, a protein can add in. This we see here, various concentrations of this one. The protein adds in very nicely. Whereas if we place an isopropyl group here, this hinders the attack. So we begin to understand from a molecular approach what's going on into a cell. And this is also a very attractive molecule because it has something very attractive kill of cell activities. And my final scientific slide is this one, which was published in Nature Friday. So now we're moving the whole things into engineered enzymes. It's done by a Chinese group here. And we're back to the basic Woodward-Hoffman paper here from 1960, an endotransition state and an exotransition state for 6 plus 4 cycloaddition. It's how to make streptomycin in living cells. Very important molecules. So they were able, by engineering enzymes, to direct this cycloaddition here, where you have this these pi systems here, to go via an exocyclic 6 plus 4 cycloaddition, predicted here, first shown in a couple of slides ago in our paper, and then a 3-3 sigmatropic cope rearrangement here to form this intermediate, which will give you the streptomycin here. So you can see you're beginning to be able to engineer enzymes based on fundamental chemical knowledge. And this brings us back to life. 90% of you are right-handed here. And you're even born right-handed. This is a baby in the mother. You're right-handed. If you move further east, Japan, out of the Pacific Ocean, 95% of the population out there are right-handed. So there's a preference for us being right-handed. And we are not the only one. Apes, monkeys are right-handed too, but it's only around 70%. And also, animals, they have a preference, only existing as one mirror image. When elephants are kissing, the trunk are always directing right-handed, as you see. So we'll take the tusk here from the narwhal. The narwhals are whales living around Greenland and northern Canada. They have this tusk being formed up to several meters long. It's always the left one who grow out. They're always rotating in the same direction. Very, very rarely they'll find one up in Greenland where both tusks are grown out. Both of them are rotating in the same direction. The elephants, when elephants are kissing, they always rotate the trunk to the right. Let us move to the snails, shells of the snails. If you look at the snails, 20,000 rotate right, whereas only one rotate left. And I can tell you, this one over here is a very, very lonely snail because it cannot mate. In order for snails to mate, they are going to have the same rotation of the shell. Here you see a left-handed and a right-handed snail here. Here they cannot mate because these two, the place they use for mating, are not located in the right position, whereas they're located right here. So the one out of 20,000 is very lonely. We are living in a right-handed society. When I give my hand here to my friend, he'll use the right hand. The whole society around us is based on that we only exist as one mirror image. The stairs in the old days were like this. They're also like this today. It's not because you're moving or you're using your right hand when walking up the stairs. No, it's because when you had to defend the building, coming from up here, it was much easier for you. You have more space if you want to fight with your enemy. And it's all over. The screws, move it to the right. Here you have a wine opener, you move it to the right because the majority of you are right-handed, and also the cars. If you're left-handed, go into that homepage here, anythingleft-handed.co.uk. You'll find things which are specific for left-handed people, and 10% of you are left-handed. I can tell you, I have a son who's left-handed. He's bought a lot of fun things here, which is very fun to have if you're left-handed and have people who are right-handed visiting you. But how did it all start? This small kid is probably wondering, why does I only exist as one mirror image? Where is my other mirror image? Far away out in the galactic system, in the summer 2016, they found chiral molecules, propylene oxide, here and here. And these chiral molecules were produced before there were life on Earth. So there has been chiral molecules in our universe before life started here on Earth. I've been talking about molecules. What about particles? In 1955, Yang and Lee, they proposed by very advanced mathematics, physics, symmetry breaking of particles. They got the Nobel Prize for this in 1957. And when they published their results, Wolfgang Pauli, he together with a very famous Danish physicist Niels Bohr, Pauli said, I cannot believe God is weak left-handed. But the theory that particles only exist also as one of the two mirror images was confirmed by Wu in 1956 by the beta emission from cobalt. So also in particles, there's a preference for only one of the two mirror image particles. But chirality in our world, in the universe we're living in, is it random? Here we have the first cell. Could the first cell, just by random, capture all the left-handed molecules? This is one possibility. Another possibility was that the first cell had an excess of, for example, the left-handed molecules. It was dividing, and then the excess of only one of the two mirror image forms of a molecule has exceeded. There were also in the third hypothesis that maybe there were formed 2 cells in the beginning, and they have been fighting, and this one to the left won. But there's also a fourth possibility, that when the first cell in our world was formed, there was one who was already taking a decision that in our society, in our world, there's only one of the mirror-image molecules, and we have this one here. I have 2 more slides, Chairman. Okay, let us look out into space. Into space, in the 50s, I think 58, there was this message from space here. This very important message from space, where they found amino acid, 90% of L-leucine, 10% of D-leucine. So out in space, it was also from this meteoroid, the same amino acid being formed as in our body. So we are here now, but molecules formed in this area here, Big Bang is here 13.8 billion years ago, but molecules formed here were also only formed as one of the 2 mirror images formed. So maybe we are living in an asymmetric universe, and there is an anti-asymmetric universe going in that direction, where you mirror image have been watching my mirror image saying exactly the same, but it's just everything is mirror image. So my last slide here is to warn you. If you're lucky, meeting your mirror image molecule somewhere around in the universe, when we move out into the universe, and your mirror image molecule wants to take your hand and say hello, I'll tell you, don't do it. Because if you do so, what will happen is you'll just be to energy in form of light. So with this, I'll finish by just showing my fantastic research group. I have a research group of 25, 30 postdocs and PhD students. They are parting, as you can see here. I've shown all the names of who are involved in the project I discussed with you. I have great support from the Carlsberg Foundation, Aarhus University, the Danish Council for Independent Research, and Novo Nordisk. And thank you very much for your kind attention. I'm sorry I took 5 minutes more than...
Sorry, we have some noise. So thank you so much for such an interesting lecture. We have time for one question. Students? Any students? Go ahead. You, yes.
Thank you very much for a wonderful journey for the organocatalysis. I would like with my question to go to the very beginning of organocatalysis.
Yeah.
The few reactions that you showed us with the electrophilic functionalization
Of aldehydes here in the alpha push.
When you draw the catalytic cycle, once the full product is formed,
Should I show the cycle up here?
well,
It might. This one.
so once the product is formed, cycle,
Here. Yeah.
functionalized aldehyde.
Yeah.
Chiral one. So maybe it's a known fact, I'm just curious. Why is it not participating again in the same cycle for new and enema? Right? The product
This one here.
yes.
Yeah. This is because now you have up here you have a proton, hydrogen sitting here. Now you have exchanged it with an electrophile. So you have now an alpha branched aldehyde. And the reaction rate between this one and this one reacting with this one is reacting much faster than this one. So that's the reason.
Yes, but if the reaction is over, you still have your catalyst in your product. So if
Yeah.
you wait,
But this is one of the advantages with this system over here. It's not coupling to alpha branched aldehyde at all.
with any kind of so it's limited to substitute with substrates, right?
Unsubstitute, yeah, but but as you can see, we also, if you move to primary amine catalyst, you can take the alpha substituted aldehydes also, and also ketones. I didn't show that.
So it's mainly sterics?
It's steric, yeah. This is the steric-based shielding of the system.
So thanks again. I hope Professor Jorgensen will be around, so any questions could be asked later through the conference. Thank you again. So, and we have a small presents from the University of Vilnius.
Thank you.
Wants to give you a small souvenir. And since we are on the auspices of Physical Technology Science Center, here's another bag.
Thank you very much. Thank you.